SpectroPhone. Today mobile phones are highly integrated systems with a variety of sensors for different applications. For instance, inertial measurement units can track the position of the phone for applications such as bubble levels, games, gestures or pedometers. Embedded magnetometers can not only be used for localization, but also detect metal in walls. Furthermore, rear cameras and flashlight LEDs can not only illuminate a scene, but also measure the heartbeat, blood pressure and hemoglobin through the skin of a finger. Interestingly, previous research has uncovered material sensing with a front-facing camera and different display color illuminations. The idea behind this is that every material has different characteristics in its light absorption. SpecCam by Yeo et al. Used 7 colors to create a set of features that produced robust classification results on 30 materials. This enables mobile device interactions with surfaces like shortcut commands or can trigger further complex actions. However, the display remains invisible, which limits the interaction capabilities with a mobile device. In this paper, we tested whether the rear camera can be used for the same purposes. Modern smartphones already include warm and cool white flashlight LEDs to produce more natural images. Since warm and cool white LEDs differ in their red and blue color distribution, they can reproduce the visible spectrum more naturally and thus be used for material sensing. Unfortunately, API restrictions not allowed us to freely control the flashlight intensity. Hence we have built an external case with embedded flashlight LEDs to test different light combinations. We collected about 30 comparable materials as used for SpecCam, and of each material we collected 30 samples. Every sample consists of 15 photos taken with the 12 megapixels camera of a Huawei P20 smartphone. Each photo was taken at ISO 800 and without autofocus in different illuminations. We control each LED in 20% intensity steps, resulting in 5 images per LED. Then we repeat the procedure by controlling both LEDs simultaneously, which results in 5 additional images. All pixels of each image are then broken down into their RGB components and divided into histograms with 64 bins per color channel as used for SpecCam. After normalizing the histograms based on the maximum value, all histogram bins are concatenated to a feature vector. Per image, 64 times 3 histogram bins are generated, which results in a maximum of 2,880 feature components for 15 images. In total, 13,500 images are contributing to our dataset, which is freely available at our GitHub repository. To test our presented application, we chose 3 flashlight configurations: warm white only, cool white only, and both light sources together. For each configuration, we evaluated 3 different illumination modes: only 100% light intensity, which we call the single mode, 20 and 100% light intensity, which refers to the dual mode, and all intensity levels in 20% steps, which we name the full mode. To exemplify, with one LED, 5 images are contributing to a sample in full mode, while with both LEDs, 15 images are involved. The calculated feature vectors of each configuration are then fed into a support vector machine for which we optimized involved parameters by grid search CV in Python. Our results based on a 10-fold cross-validation show that we can achieve comparable recognition rates to SpecCam but with fewer images. Thus, we can reduce the sensing time and keep the display visible for further interactions. For example, we could filter displayed notifications based on the material the smartphone is lying on. In home office, people could use this technology to mute private messages when the smartphone is placed on the desk. When placing the smartphone on the coffee table, the messenger status could then automatically change to available. Since a manufacturer already integrated a molecular scanner into a smartphone, we envision that in the future smartphones might be capable of identifying counterfeit clothing. However, in order to test our app in this scenario, large amounts of data would have to be collected. A small window of neoprene that seals the camera and flashlight on the clothing could then prevent ambient light from interfering with the measurements.